Hey everybody, Mr. Alent here again. Just here going over our current section, Unit 9, Section 1, which is going to be covering exponential functions. Hope you guys are doing well. I really recommend that you do these notes with me. So if you get out a piece of paper, write this down. This could help you out as you work through this section, especially since this is new content for us. So here's what an exponential function just kind of basically looks like, where we have our f of x equals b to the x, where b you can kind of b stand for base right now, but it's like a constant. It's a constant number, and the x, there's that exponent, the variable. So the variable is the exponent, is what makes a function exponential. Okay, so when the variable is the exponent. So here's what an example of that might look like. If I have f of x equals, let's go with 2 to the x. It's a very basic, very common exponential function, one that's used quite frequently. And what I want to do is kind of get an idea of what do these look like graphically, right? So let's build a little table. One of the best ways to graph something is just go ahead and build a table of values and see what it looks like. All right, so we're going to pick, remember you always pick your x values that you're going to plug in and see what you get out. So let's pick some negative and some positive and just kind of get a view of our function here. And then remember those are your inputs, these x's that we chose, so we're going to plug them in for x and see what comes out when we do that. We're evaluating the function for these values. So the function is 2 to the x, so 2 to the negative 2. Now, you have to remember some old rules when you're dealing with exponents and negatives. The negative in the exponent does not mean this is the negative number. What it means is we want the reciprocal of this. So 2 to the negative 2 is the same as 1 over 2 squared. And notice there's no negative there now because now I've applied the reciprocal. And then what is 2 squared? 2 squared is 4, so this is 1 over 4. It's 1/4. Okay, so 2 to the negative 2 is 1/4. 2 to the negative 1, again, we're going to apply the reciprocal, so 2 to the 1, but 2 to the 1, any number to the first power is itself, so this is just 1/2. Okay, and then we've got 2 to the 0. Any number to the 0 power is actually nicely just 1. Any number to the 0 is 1. And then we have 2 to the first, right? We're just kind of going a little bit faster here. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. And 2 to the fourth is 16. So let's go ahead and graph this. Let's build a little axes here. See how well Mr. Allen can draw straight lines. That was okay. Not great, but okay. Alright, so we got our x and y, or f of x, right? We always call it the y-axis, but it's, remember you can replace that with the with y. I'm just going to put scale on here. Okay, something like that. Alright, and we'll go ahead and graph them. I'll use a different color for that. So we've got negative 2 and 1/4, right? So that point, negative 2, 1/4. Negative 2, 1/4 is right about there. We got negative 1, 1/2. We've got 0, 1, 1, 2, 2, 4, 3, 8. Let's see, 1, 2, 3, 4, 5, 6, 7, 8 right there. And then 4 is a 16, which is off my paper right now, which is fine. And you get this curve, and it is curved, so don't do like a zigzag connect the dots, right? It's a nice curve that's going upwards to the right, and it starts going very steep, and then probably even steeper than how I drew it, because if you again think about the next one, 4 is going to be all the way up to 16, way up here somewhere, right? And then the next one would be 32, and it grows really fast. So a couple things to note about the graph here. Again, it is a nice curve. We are going to go very steep on the right side. On the left side, now that's the part I want to talk about. The left side, what you need to be very careful of when you're graphing is do not cross the x-axis. Why? Why don't we cross the x-axis? Why did I draw it this way? By the way, this does not curve back up. It is getting really, really close to the x-axis, so we're getting closer and closer to the x-axis. The reason we don't cross, though, is think about over here, right? If I chose, like on an x here, let's say I chose like negative 100, right? So some really big negative number, big magnitude-wise. 2 to the negative 100 is 1 over 2 to the 100, which is a really, really tiny number, but it's still a number bigger than 0. So because that's still bigger than 0, this is going to get really, really, really close to the x-axis, but we're never actually going to cross it. We're not going to cross the x-axis. We're not going to get to an output of 0. No matter how tiny these numbers get, we're never going to have an output of 0. The only way we would is if we did some kind of vertical shift, if you remember back to transformations, where we had some number being added or subtracted from here, in this case it would be subtracted, to make it cross. Without that, if there's nothing over there being added or subtracted, no vertical translation, we do not cross the x-axis. Okay, that's an important piece. Now, when we're talking about exponential functions, there's really two types that we talk about. We talk about what's called growth, and we talk about decay. All right, so growth is like the example we just saw, like the above example. That's an example of growth. And how you know you're dealing with growth is it happens when your b value is greater than 1. And the b, again, that goes back to up here. When this number that's being raised to the power is bigger than 1, that's going to be growth. Okay, so like here, 2 is bigger than 1, it's being raised to the x, so this is going to be growth. When does decay happen? Decay is going to happen when the b value is between 0 and 1. All right, so when b is between 0 and 1, what does that mean? It's a fraction, it's a decimal that's bigger than 0 but less than 1. That's when it's going to be decay. Growth, obviously, we were increasing our value, right? This number started small and just kept getting bigger and bigger and bigger. Decay is losing value, and so it'd be basically the reverse of this. It's going the other way. We would start, as we increase our x values, our inputs, we're going to be losing value. Okay? And so let's see an example. Kind of like we graphed a growth, let's graph a decay. So here's an example we're going to use for decay. I want to do, it'll keep it very similar. We're going to go with 1/2 to the x. So that's one way you could see it written. You could also see it written as like 0.5 to the x. Sometimes you'll see the decimal, and that's fine. I'm going to use the 1/2 as far as the table. I think it's going to help making the table a little bit easier. And so, like before, yeah, we're going to graph, so let's make a table. So x and f of x. So I'm going to go with -3, -2, -1, 0, 1, 2. All right, -3. Okay, so again, apply those same rules. We're going to take this 1/2, raise it to the -3rd. But again, a negative means reciprocal. Reciprocal means flip, so 1 over 2 gets flipped to 2 over 1 to the +3rd now, right? We flipped it so we can make it positive. Well, 2 over 1 is just 2, and 2 to the 3rd is 8. Okay, 1/2 to the -2. That's the same as 2 over 1 to the 2nd, which is 4, right? 2 squared is 4. 1/2 to the -1. Again, it gets flipped to the +1. Well, it's just 2 then. If it's to the first power, it's just 2. 1/2 to the 0. Okay, no more flipping, no more negative exponents, so no more flipping required. 0 to the 1/2 is just 1, right? Anything to the 0 is 1. 1/2 to the first is 1/2, and 1/2 squared is 1/2 times 1/2 is 1/4. So really, it actually is, I mean, if you think of the tables of the growth up here to this one, they are exact kind of mirror images of each other, and that's because one is the reciprocal of the other. And so let's go ahead and graph this one. Graph our decay here. All right, pick a scale. Okay. And we'll plot those points. So negative 3, we're up at 8. 1, 2, 3, 4, 5, 6, 7, 8. Negative 3 is way over here. Negative 2, we're at 4. 1, 2, 3, 4. Negative 2. And negative 1, we're at 2. 0, we're at 1. At 1, we're at a half. And at 2, we're at 1/4. And so again, that's what I was just saying. You kind of see it's a reflection. You know, if you think again transformation-wise, we just reflected really over the y-axis. It flip-flopped over the y-axis from our growth to our decay. Right? So this time, as we're moving to the right, we're getting really close to the x. We're getting smaller and smaller. We're losing value as we move in the positive direction. Okay? So there's growth and decay. Now, I also want to talk about the forms that you'll see this in examples, especially when you're dealing in like real-world situation. Like when is this used? And by the way, guys, this is heavily used. It's very applicable in science. If you talk about growth of bacteria, virus. I mean, right now we're talking about the coronavirus, right? Virus growth, and a lot of things grow exponentially. As far as nature, or decay exponentially if you talk about decay of any kind of nuclear substances or whatever, so or radioactive substances. And so when it comes to growth, here's the general formula we use. A of t equals a times 1 plus r to the t. Okay, and I'll show you decay in a second here. Okay. And then let's talk about those pieces. What is the A of t? Well, that stands for basically your final amount. You know, after we've done this stuff, we'll get some final amount of the thing we're talking about. And again, that's kind of contextual. It depends on the problem. The A up there, that little a, that stands for your initial amount. This is how I started. How much did I have at the beginning? My initial amount. Okay. The 1 plus r. Now the r is coming from what we call the rate. And the rate is always written as a percentage, or almost always given as a percentage. I want to talk about that in a second, but let's also talk about what t is. T stands for time, as it kind of makes sense there, right? T is for time. And it's a time period. It depends on the context of the problem. Time could, I mean, this could be any number of things. This could be seconds, minutes, hours, could be days, it could be years, months. It just depends on the context of the problem, what the time stands for. But it's always a period of time. Okay, let's come back to the rate piece. The rate is written as a percentage. So if there was like some example of that, a quick example, like let's say my rate of, you know, if you're talking about like a savings account maybe, you know, I've put some money, that would be my initial, into some savings account, and it's going to grow at some rate. Let's say, I don't know, 3%. That's actually pretty good for most savings accounts. Most savings accounts are much less than that. But let's say we had a 3% rate on our savings account. Now, I would not, and here's what I want to emphasize, I do not put in a 3 for R. This is not 1 plus 3 making 4. That is incorrect. We always think of percents. If we're dealing with any kind of mathematical formula or equation, you want to think of it in its decimal form. 0.03. All right, 0.03 is 3% as a decimal. That's the number that goes in here. So this would be 1 plus 0.03. Right? And that's, and really what you're thinking of, this is again a growth. And so this 1 is coming from like 100%. So 100% of my initial amount plus an additional 3% of my amount is what's going to grow every time period. Every time period I'm having an additional 103% of what I had previously. Okay, the decay formula, it looks almost exactly the same. The only difference is that instead of adding the rate, we're going to subtract the rate. Right, we're going to lose value, right? So if I had this in the other way, let's say you bought a car and its value decreases every year you have a car by, let's go with the 3% again. So this would be 1 minus 0.03 is a 0.97. So every year that I've had the car, I am at 97% of the previous year of what its value is. Okay, I have to end the video. I'm almost out of time. So I hope that works. One thing I want to say too, don't forget about PEMDAS, order of operations. Okay, don't forget about PEMDAS. When you have these formulas, you do the exponent piece first. Do not multiply a by this value and then exponent. Exponent comes before multiplication. All right, guys, good luck. Do the best you can. We'll talk to you later.